Good afternoon. This is Math 2413. This is November the 8th. A couple of announcements here at the beginning of class. Homework 4. I sent an email out a day or two ago about some technical issues I had, and then with uploading videos, which I'm still kind of dealing with. I did get the Monday lecture uploaded eventually yesterday. And this, if you're watching this video, that means I've got this one uploaded also, but right now I'm having trouble with uploading again, so hopefully things don't get delayed too bad. But in the email, I did announce that homework 4's due date I would postpone till November the 10th. Please get this finished. Don't get behind on your homework. Send that to me as an email, attachment to an email as one PDF file. And please try to work on that and get that turned in. Don't hesitate to email me if you have questions. Don't hesitate to come by my online office hours if you have questions. I'd be happy to help you out. So that's due November the 10th by the end of the day. Exam 2. I'm in the middle of grading your class right now, and so I should have those finished today. I definitely intend to have those grades posted later today. Email me if you want a copy of the graded exam. Online office hours, please take advantage of those online office hours. Come on by for help. I'll be online this evening from 8 to 9, Thursday, tomorrow afternoon 1 to 2, and Sunday 7:30 to 9. So please take advantage of those office hours and come on by for help. Today, we're going to go ahead and start in on Chapter 5. We're going to briefly touch base with what we've talked about last time as we finished up Chapter 4. And today we'll get into Chapter 5 and start talking about areas underneath curves and the definite integral. And so let's go ahead and just jump right into that and get started. First of all, last time, remember, we were talking about antiderivatives and the indefinite integral. Remember that the indefinite integral, the notation for that looks like this. This is the way we would typically write an indefinite integral. And this is simply defined as the set of all antiderivatives for little f of x. And so remember, the antiderivatives, an antiderivative is a function, capital F, whose derivative is equal to little f. Right, so we went through a bunch of basic properties for calculating antiderivatives for various different types of functions. And so just briefly kind of touching base with that again. Recall that with a polynomial like this one right here, to write the antiderivative down, we're using the power rule and the sum difference rule and the constant factor rule. And we are evaluating the antiderivatives or the indefinite integrals for each one of these terms individually. And then the constant factors in each case can come out in front as a factor from each integral. So ultimately, this is the problem that we would be looking at or tackling in this case. That last one would be a 1 right there. We typically don't write that step out, but that's really what we're doing. And then in each term here, we'd be using the power rule. And so we have 1/4 x to the 4th minus 2/3 x cubed plus 3x squared minus 8x. And then please don't forget the arbitrary constant at the end plus c. So remember, the power rule states that when you find an antiderivative for x to the n dx, that's 1 over n plus 1 times x to the n plus 1 plus c, that there is one power where that power rule does not work, and that's when n is -1. And when n is -1, then you have you use the log rule instead of the power rule. So in this problem, if we have the square root of x plus 1 over x dx. First of all, the first term is the power rule, right? We would write that as x to the 1/2. We're not finding an antiderivative yet. We're just dealing with how this function is written, so we can use the rules that we have for antiderivatives. And so this second term, this 1 over x, that's when n is -1. That's that the 1 powered where the power rule does not extend to, right? You have x to the -1 in that last term. And so we just leave that one alone and leave it as 1 over x. And we're ready to write the antiderivative down for that. So this first one, using the power rule, add 1 to the exponent. And so you get x to the 3/2, put the reciprocal in front as a factor, which would be 2/3. And then the second term, we're just finding the antiderivative for 1 over x dx, and that would be the natural log of the absolute value of x plus c. Remember, that's our log rule right there. So we've talked about the power rule and the log rule. We've looked at trig functions, so if you have the antiderivative for cosine of 3x dx. First of all, the antiderivative for cosine is sine, but remember that because it's 3x, we've talked about the idea that you get the reciprocal of that constant in front, and so this would be 1/3 times the sine of 3x plus c. Don't forget, you can always differentiate that function that you get, because that's supposed to be an antiderivative for cosine of 3x. And so you could find the derivative of 1/3 sine 3x, and you'd find that you get cosine of 3x. So you can always check your work, remember, in these problems. You can always do this by taking the derivative of the antiderivative you've written down and making sure you get the original function back when you do that. Right? So we would take the derivative of this function, and we would get just cosine of 3x at the end, because the 3's are going to cancel out. So, all right, and then we also looked at exponential functions. So we have e to the 5x, and we're looking for the antiderivative for that function, right? We would see that that's 1/5 e to the 5x, that you always get the function itself back, just like you would with derivatives, but then you get the reciprocal of that coefficient in front, like that. So you have a 1/5 e to the 5x plus c. And then finally, we looked at the antiderivative for something like this, where you have dx over the square root of 1 minus x squared, and we saw that this was an arcsine. This is arcsine x plus c. It's just turning around the derivative form for arcsine, and when you turn it around, you get an antiderivative form. So those were all problems that we looked at last time. Okay, and we did a lot of examples last time. Definitely some practicing that you want to do there, and I'll probably send out some practice problems over the weekend, some additional problems beyond what's in your textbook, so that you have more practice. Nothing that will be turned in, but just, I think right now the more practice problems you can get on antiderivatives, the better off you're going to be. All right, so that's what we talked about last time. So now our goal today is to look at a different type of integral. So here we examined the idea of an indefinite integral as the set of all antiderivatives, and this was our notation for the indefinite integral. So today our goal is to talk about a different type of integral than this one. And so now we're not ready to deal with that yet, but we're going to get to that relatively quickly. So we start this lecture off with a geometric question. And the geometric question is this: if we have a function and the graph of a function, like I'm picturing right here, so let's say we get this graph of this function f of x, how do we go about calculating the area that is bounded by that curve between x equals a and x equals b and the x-axis? So we're looking at the area of this region right in here that I'm shading. Now the problem with this, because it seems like a relatively straightforward question, but the problem is this region that I'm shading right here is not a nice regular region. It's not a rectangle, it's not a circle, it's not a triangle, it's not a trapezoid, nothing where we have a nice geometric formula where we can calculate the area. And so that's our question here, is how do we calculate an area of a region like the one pictured above. Now this is not necessarily a straightforward question at all. And so what we're going to do is we're going to, our strategy is going to be this. What we want to do is use a geometric figure that we do know the area of and use that to help us approximate the area underneath this curve. So we're going to use a regular geometric figure and using that regular geometric figure, we're going to evolve a process where we can approximate the area of the region above. All right, so now what I'm going to do to kind of start talking about this strategy is we're going to start with a nice function that we actually know the function. And so I've got a picture of it right here. This is the function f of x equals x squared plus 1. And what I want to do is I want to approximate, or I want to find, actually, not approximate. Our goal here is going to be to find the area bounded by f, the x-axis, the x and y-axis, and between x equals 0 and x equals 2. And x equals 0 is really just repeating the idea that I just talked about, the y-axis right here. So on my curve here, we're looking at this region right here, bounded by these dashed lines and the x-axis. And we're going to try to hatch a scheme where essentially where we can find the exact area underneath this curve. This is what we're after. So we have a nice function here. We know the function, not a difficult one to graph. It's a simple one to evaluate. And so this is our goal, is to try to find this area. Okay, and so the scheme we're going to use is we're going to use rectangles to do this. And we're going to use rectangles because we know the area of a rectangle. So we're going to use rectangles to approximate this region, to approximate the area of this region. Okay, so what we're going to do is we're going to divide up the x-axis into intervals, and we'll make these intervals. We're going to divide it up into 4 intervals here. So these are sometimes called subintervals. We're going to divide the interval from 0 to 2 is the interval, and so these would all be called subintervals. 4 subintervals. The width of those subintervals, in this case, is 1/2. And in general, we call the width delta x. It's the change in x there. And so that would be delta x in any of these problems that we're going to talk about. So this distance right here, we refer to as delta x. And notice that the width of each of these intervals is going to be exactly the same. And we do that as a simplifying assumption in this problem. You don't have to do that, as it turns out. You can make the subintervals, all different widths, and that would be fine. You could do that. But we're going to simplify the process by making them all exactly the same width. And then what we're going to do is use those subintervals to create bases for rectangles. So we're going to use the subintervals to create bases for rectangles. So these rectangles are going to sit above each one of these subintervals. And I say the bases, but so that would be the widths of these rectangles right there. And then to establish the height, what we're going to do is we're going to use where the curve is at the left-hand endpoint of each of those subintervals. So we're going to use what we call left-hand endpoints. And we're going to use the function values at those left-hand endpoints to actually create rectangles. All right, so now the first subinterval goes from 0 to 0.5. And so the left-hand endpoint there is at 0 right there. See, and that red line there is going to establish the height of the first rectangle. The second rectangle will be above the second subinterval, and we'll use its left-hand endpoint. And so that left-hand endpoint would be like this, and that's going to establish the height of that second rectangle. And we keep on going. The third subinterval, that's its left-hand endpoint. We go up to the curve, and we're going to use that line segment for the height of that third rectangle. And then finally, in the fourth subinterval, the same thing, the left-hand endpoint. So those are all left-hand endpoints. And so to finish this picture, this is all you're doing, is you're just completing the rectangle. You just go over to the next subinterval in each case. And when you do that, you're creating these rectangles here that fit underneath our curve. All right, so what did I do? I used 4 subintervals, and because the total interval was 2, right, the width of the total interval was 2, if I divide that by 4, I get 1/2, right? And so that's how we got that delta x. And from the picture, it was pretty obvious here. So let me complete this last rectangle right here. All right, so if we calculate the areas of each of these rectangles, now we are not finding the area of the shaded region like we wanted. Definitely not. This is an approximation, maybe not a very good approximation, but it is an approximation for that area. And what we're going to do is we're going to see if we can improve upon this approximation. So we're going to calculate the areas of those 4 rectangles right there. All right, and so to calculate those, what we could do is we could write out this expression that the area, we'll say, is approximately equal to, and the first rectangle, its height, remember we used the left-hand endpoint, which was 0 in that first subinterval. And so the function value gives us the height, and that's just f of 0, and that would be times 1/2. And so that is the height of that first rectangle times its width. It's height times width in each case. So that would be the first rectangle. The second rectangle, the left-hand endpoint is at 0.5. And so this would be f of 0.5. Probably, you could use 1/2 there. Either use fractions or decimals. That would be fine. And that'd be f of 0.5 times 1/2. The next subinterval, the third one, we used the left-hand endpoint there, which was 1. And so this would be f of 1 times 1/2. And let's look at that third rectangle, that third subinterval there, to kind of be clear about what I'm doing, is that this distance right here on the third subinterval, that's given by f of 1. Right? We take our function, which is x squared plus 1, we evaluate at 1, and we get that height. Right? And then the width certainly is just this distance right here, which is 1/2 for all of the rectangles. Finally, the last one, we would have f of 1.5 times 1/2. And so that arithmetic problem right there would give us the our approximation. Now, one thing we could do here to make our lives a little bit easier is we could factor out the 1/2, because that 1/2 is in every term. And so notice all we're getting is these function values added together. We just get all the 4 of those function values added together, and then we multiply that by 1/2 at the end. So you go through here and you do the arithmetic. So f of 0 is equal to 1, and then f of 0.5, right, is 5/4 or 1.25. F of 1 is equal to 2, and f of 1.5 is 2.25 plus 1, 3.25. Or if you wrote it as a fraction, it'd be 13/4. And that'd all be times 1/2, or 0.5 if you wanted to write it that way. So when you do this arithmetic here, you get the area and do all this arithmetic, multiply by 1/2. You get 30/4, I'm going to write it as a fraction, times 1/2, or you get 15/4. And that's our first approximation. And what do we do here? We use 4 subintervals. We use 4 subintervals. Whoops. Let me write subintervals here. 4 subintervals. And to calculate the heights of those rectangles, we use the left-hand endpoints. And so when we use those 2 things to draw the picture, we get our approximation to be 15/4. And now, what's certainly true when you look at the picture, it's absolutely, positively true that 15/4 is too small, right? Just based on the picture, there's no way that has to be smaller, because you've got all of these regions sitting here that I'm shading in blue that you're not getting when you draw these pictures, right? And so these shaded regions here would represent the error in our calculation right here. Right? We're not getting those regions right there. Okay, but this is a start, and we've got a number that's an approximation. It's too small. That's fine. So let's see if we can modify this. So one way to modify this would be, instead of using left-hand endpoints, use right-hand endpoints. So we could use right-hand endpoints if we wanted to. So let's use right-hand endpoints to determine the heights of those rectangles. So use right-hand endpoints and still use 4 subintervals. So let's see how changing from a left-hand endpoint to a right-hand endpoint for each of these subintervals changes the way the picture is going to look. Okay, so again, here's my region. Let's go ahead and shade this in here. So we shade this region. And certainly don't have to shade it, but I do want to shade it just so that it really stands out. That this is what we're trying to find the area for, this region right here. Okay, so if we're going to use right-hand endpoints, then the right-hand endpoints in this case would be 0.5. That would be the first. Here's a subinterval right here. Whoops. Here's a subinterval right here, and the right-hand endpoint of that subinterval is at 0.5. So what we do is we go up here to 0.5 like this, and we're going to use that to determine the height of our first rectangle. And then we're going to use that point to determine the height of the second rectangle. This point right here, 1.5, to determine the height of the third rectangle. and then this point right here to determine the height of the fourth rectangle. Okay, so when we do that, when we draw our picture is going to look different. Here's the first rectangle right here in our first subinterval. And notice its height is different than the one we started with in the last when we used left-hand endpoints. And then we keep on going. We use right-hand endpoints and draw these pictures out. Right? And this is the way this picture is going to look. So distinctly different than the first one. Same basic idea, but definitely different. And in this case, what's going to happen, this is clearly going to be too big, isn't it? When we add these rectangles areas together, clearly too big, because now we're getting these regions that are sitting above the region we're trying to get. So what I'm shading in blue here now is going to be our error in this case, and it's going to be too much, right? When we add these areas of these rectangles together, we're going to get something that's too big. So our calculations would go like this in this problem, that the area, and we can kind of go to school on how we wrote this out last time. All we have to do, we know, is add these function values together and then multiply by the width out here, 1/2, because that width is going to be part of each calculation. So the first function value is at 0.5. That's the height of the first rectangle. The height of the second rectangle is f of 1. Height of the third rectangle is f of 1.5. And let me emphasize that that is the height of the third rectangle right there. And so that would be f of 1.5 right there. All right, so that's f of 1.5. And then finally, the last rectangle, this would be plus f of 2. Right, that's the height of the last rectangle there. So our arithmetic is certainly a little bit different here. So our area calculations in this case, we'd have 1.25 plus 2 plus 3.25 plus, and then finally the last one we have a height of 5 times 1/2 like that. And we get, if we do that arithmetic, we get that our area is 23/4. So we know certainly from the picture this is going to be too big. Now, one thing we clearly know from these last two screens is that the actual area must be between the two numbers that we got. Must be between, and what do we get on the first one? 15/4 and 23/4. Like so. It's certainly got to be between those two. But one thing I wanted to do with these two pictures from these last two is show you the difference between using left-hand endpoints in the region and using right-hand endpoints in the region. And so now, if we want to change this procedure still more and maybe get a different approximation, hopefully a better approximation, what we could do is we could certainly use more rectangles. I use 4 rectangles in each picture. What if we use more rectangles? So what if we started with more subintervals? So let's let the number of subintervals in general, let's let that be equal to n. Okay, that would be the number of subintervals. All right, so in our first two examples, n was 4. So let's make n equal to 8 in this case, in our problem here. Okay, so let's let n equal to 8. And let's continue to use right-hand endpoints. Now, that is simply kind of a simplifying assumption there that we're going to use either the left or the right-hand endpoints. And in general, we're going to probably use the right-hand endpoints to do this. But It doesn't matter. You can use the left-hand endpoint, right-hand endpoint. You could use the midpoint. You could use an arbitrary point in each subinterval and still accomplish the same thing that we're doing. We could still generate an approximation like we've been doing. Okay, I'm just doing right-hand endpoints to calculate the heights of these, just to make our lives a little bit easier, quite frankly. Okay, so now if n is 8, now the total interval, so what is delta x going to be in this case? Well, delta x, remember, is the width of each subinterval. And the width of each subinterval would be our total interval, right? The total length of that interval divided by n. So what's our total interval in this case? Well, we're going from 0 to 2, so technically 2 minus 0, or 2. And we divide that by 8, and we get 1/4 in this case. So delta x in our problem is going to be 1/4. That's the width of each of these subintervals. And so if I go through here and I look at 8 subintervals, notice each one is going to have a width of 1/4. There are my 8 subintervals. Each has a width of 1/4. And I'm going to use the right-hand edges for each of these to calculate the heights of the rectangle above each subinterval. So I draw in these line segments here at each of these right-hand endpoints, and these line segments are all going to determine the heights of the rectangle in the subinterval before that. So we've got a ways to go here. We've got a lot of drawing to do. I will ask you on the next exam to make a drawing like this. I will not ask you to do this probably for 8 subintervals, just because it's kind of a long process to do this. Oops, and I didn't need that last one there because I'm only going up to 2. There you go. And I can erase these marks right here as well. Okay. So all right. So if you complete those rectangles, this is the way the picture looks, right? You have that this rectangle right here, over the first subinterval, and then this one over the second, this one over the third, over the fourth, and so on. Finish this picture out. Now, we're definitely hopeful that this is a better approximation. And why are we hopeful that it's a better approximation? Well, the error is still there, right? And there's more pieces to the error, but the error is much smaller than it appears to be in the previous examples, right? So those pieces, there's more of them that are sticking above the curve there, but they're all a lot smaller. So we're expecting that this is going to be a better approximation. So what would our area be in this case? Remember, we've seen that all we have to do really is add these function values together and then multiply all those function values by the width of each subinterval, each rectangle, and that would be 1/4 in this problem, right? And so you'd have f of 1/4. I'm just going to use fractions all the way through this, plus f of 1/2, plus f of 3/4, plus f of 1, plus f of 5/4, plus f of 3/2, and going to kind of sort of run out of room here, so I'm just going to erase this and continue to write these, plus f of 7/4, finally plus f of 2. And really all you think about that, all you're doing is counting by 1/4. If you think about it that way, this is just 1/4, this is 2/4, 3/4, 4/4, right? All you're doing is counting 5/4, 6/4, 7/4, 8/4, which ends up being 2. Right, so you're just counting by 4ths in each case. And then what's this going to be multiplied by? This is all multiplied by the total width of the of each subinterval, because you're calculating area, so it's always height times width here. And I need to put a squiggly equal sign in the front because this is an approximation right here. When you go through this all this arithmetic, and I've done that for you already, when you go through all this, we get 83/16. And 83/16 is, in fact, between the previous two examples we got. Remember, we got 15/4 and 23/4. So 15/4 and 23/4. So as sixteenths, if you wrote everything as sixteenths, the first one would be 60/16, and this last one would be 92/16. Right, getting a common denominator. So 83/16, what is it doing? It's sitting between these two. And that should definitely be the case. And we expect that this is a better approximation for the area. So this idea of expanding the number of subintervals, increasing the number of subintervals, seems to be a procedure that would allow us to improve our approximation. All right, so then the idea is this then. So let's instead of saying 4 subintervals or 8 subintervals or something like that, let's just use n subintervals and generate a more general expression for the area using n subintervals. So we're going to generate a more general statement for the area. And to make our lives a little bit easier, let's just use right-hand endpoints for these in each case, right-hand endpoints. So the idea goes like this. If you think about our picture, and let's go ahead and pull that picture up again from our photo album here. Let's go ahead and flatten that and paste it right there. So if we remember, this is the region ultimately we're after. The region from 0 to 2. We're trying to find that area. So if we start just using n subintervals, then I want you to think about what the width of each one of these is going to be. If we use n subintervals, well, the total interval, again, is 2 minus 0 divided by, and then it would be n of them. So we divide by n. Remember, on the first examples, we used 4 subintervals, so we took 2 and divided it by 4. The last example used 8 subintervals, so we took 2 and divided by 8. So now we're going to take 2 and divide it by n. So the width of each one of these subintervals is 2 over n, and that would be our delta x. And as we count, we're counting just like we did a second ago on these subintervals. We'd have 2 over n, 4 over n, 6 over n, 8 over n. We're just counting by 2 over n's here. And so what we come up with for our approximation, and we're going to kind of look at each one of these subintervals here. So the first subinterval is going to be written, and I'm going to start with this endpoint right here, 0. And what are we doing? We're adding 2 over n to get to that first value. So this is f of 0 plus 2 over n. That's just f of 2 over n, I know that. But I want to put in that far left edge of our big interval, because that's where we're starting the counting from. We're starting it from 0. So you have f of 0 plus 2 over n plus f of 0 plus, and there's 2 over n's now. So that'd be f of 2 times 2 over n. And there's a reason why I want to write it that way instead of 4 over n. And then plus f of 0 plus, and now the third one, there'd be 3 of those 2 over n's. And we'd keep on going like that until the very last one And there would be, we start at the far left, which is 0. We add n of those 2 over n's at the end right there. And n times 2 over n, the n's divide out, you get 2, and plus 0, you get 2, which makes sense. That should be our left edge of the big interval there. So those are all the function values. And what are we doing there? We are multiplying by the total width here. And the total width, remember, that's delta x, total width of each of those subintervals, which we said was 2 over n. All right? Our calculation was just above right there. Now that's a long, nasty, ugly expression to have to write out every time if you're going to write out all these function values in this sum. So what we do here is we use sigma notation, right? This is called sigma notation to abbreviate this sum. So sigma notation, notation to abbreviate the sum. In other words, write it in a more concise form. And so in sigma notation, you use the Greek letter sigma. That's my Greek letter sigma, which is not all that great, I understand. And what we're going to do is we're going to write the general statement out for each of those function values. So that'd be f of 0 plus, and the number that's counting, the counter in this case, is how many 2 over n's we're going to use. Right? That's our counter in this case. We've got 2 of them here, 3 of them here, n of them here. Technically, 1 of them in the first function value there. So you have 1 of them, 2 of them, 3 of them, 4 of them, and so on. That's our counter. And so we're going to write that as I. We'll use I as our counter here. Times 2 over n. And then that would be multiplied by 2 over n, our delta x value. Like that. And then the counter, what does it do? The counter goes from I equals 1 to n. It's a much more concise way of writing that. That sigma notation means a sum. And what we're doing is we're adding n of these terms together. And the I is our counter. That's what's changing in each one of these terms. And again, I used an equal sign there, but this is just our approximation for this area. And what does n represent? N is the number of subintervals. Remember, n is the number of subintervals. All right, so that gives us a nice kind of form to use when we look at a problem like this. And so if we wanted to do this kind of in a general way, then, for the problem that we're talking about, then we could write this out. And so we're going to use our function and actually use this sigma notation to actually come up with an expression in terms of n that would give us the area underneath that curve. Then presumably when n was 4, we would get our first approximation that we got a few minutes ago, which was 15/4, right? This was when n was 4 right here. This, and then this is when n is 8. Remember, the 23/4 is with left-hand endpoints. And we're using right-hand endpoints for this expression we just wrote at the very bottom right here. Okay, so we go to our function f of x. We write it down, x squared plus 1. And we've got this general expression that we've kind of written out, that the area is approximated by the sum as I goes from 1 to n of f of 0 plus I times 2 over n times 2 over n, which is the width. And remember that these function values, these are the heights of the rectangles, and 2 over n represents the common width for each rectangle. So each one has the same width, 2 over n. All right, so if we try to get a handle on this expression, and it's messy algebraically, I'm going to warn you about that. First of all, that 0 is no longer necessary to write down. So we don't need to do that. So this is just going to be I times 2 over n, f of I times 2 over n, and then this is times 2 over n, like this. Okay, so now we evaluate the function. So now we'll get a handle on the sigma at the end here, so don't panic on that. We just keep on writing it down because it's a sum each time. So this would be x squared plus 1. In place of x squared, we put I times 2 over n. I times 2 over n squared plus 1. And there's our function value. Put that in brackets, and then this would be times 2 over n. Okay, so now we follow along with the way the algebra here. And so this is going to be I squared times 4 over n squared. Just square everything right there, plus 1 times 2 over n. Now you can leave the 2 over n out there, or you could go ahead and multiply through by that 2 over n. And one thing, I started writing wrong for some reason. I put n's here, but this should be i's in each case. So I apologize for that. These are all i's going from 1 to n. I is our counter. All right, so now I'm going to go ahead and multiply through by that 2 over n. You wouldn't have to do that at this point, but I'm going to go ahead and do that. So you have 8 over n cubed I squared plus 2 over n, like that, when you multiply through by that 2 over n. And now what we're going to do is we're going to, eventually we want to get rid of the sigma notation. I'm going to show you how to do that. So we're going to break this up as 2 sigma notations. If these sums both exist, then this would be a legal thing to do, is to just sum each term separately. Now at this point, it gets a little bit dicey, a little bit tricky, but the variable in this sigma is the I. That's our counter. That's what's changing. The n is a constant. And so these sigma notations have the property that constants can be taken outside of this sigma, and you just leave the variable part inside. So the first term, just the I squared, gets left inside the sigma. The second term, notice the 2 over n just comes out just like it is, and you're left with 1 right there. All right, so now these sigmas right here, there are known formulas in terms of n for sigma statements like these right here. And now it's certainly not something where I would require that you know these formulas from memory, but these are in your textbook on page 514 of your textbook, and they go like this, that the sum, if you have a sigma notation like this, that the sum as I goes from 1 to n of 1, well, that's just equal to n, because all it is 1 plus 1 plus 1 n times. So you could take, if you have a sigma, a sum of 1 as I goes from 1 to n, you can always just replace that with n. And then if you have the sum as I goes from 1 to n of I, you can use mathematical induction to prove that that's n times n plus 1 over 2. So if you have a sigma that's the sum as I goes from 1 to n of I, you can always replace it with the algebraic expression n times n plus 1 over 2. And then for I squared, the formula for the sigma notation with I squared is that this is n times n plus 1 times 2n plus 1 over 6. The expressions get more and more complicated. Now for these problems, these are the only formulas I'm going to ask you to be able to use, but I'm again going to give you these formulas, okay, on the next exam. So what we do is we take those formulas and we literally just substitute them in place of the sigmas here. And notice when we do that, we're done with the sigma notation, and all we have is an expression that involves n. So that I squared gets replaced with n times n plus 1 times 2n plus 1 over 6. And the sum as I goes from 1 to n of 1 just gets replaced with n. Right, all you're doing is substituting those expressions in. And notice the sigmas are gone, and now all you're left with is an expression that involves just n's. And on the first one, let's see, the n's divide out, and the 8 and the 6 divide out and give you a 4 over 3. So you have 4 times n plus 1 times 2n plus 1 over 3, over 3n squared. And then the second one is just the n's cancel. I'm just left with plus 2. And so you have this little formula right here that actually gives you the area underneath that curve, the approximate area underneath that curve for n subintervals. So this is the approximation for the area under f of x equals x squared plus 1 between 0 and 2 using n subintervals and right-hand endpoints. All right, so now, that expression right there, we should, if you used n equals 4, remember when n was 4, going back a couple of screens ago, right, we got 5/4 for the area. So this formula that we've just generated here, if we pick n equals 4 here using this formula, then we should actually get that 15/4 as an answer. We should get exactly 15/4. Right? For any number of subintervals, this formula should work out for this particular curve, right? And you could verify that if you wanted to. Let me go ahead and kind of copy this formula down right here. And actually, let me go ahead and use these words in here too, and I'm going to copy those as well. So we're going to go ahead and copy that. Now I'm going to try it one more time. So bear with me if you're watching the video. So I'm going to copy that. I'm going to go to the next page. I'm going to paste that right there. And there's our approximation. So when n was 4, so in other words, when we use 4 rectangles, then this approximation for area, we'll just put a sub 4 right here, would be equal to 4 times 4 plus 1 times 2 times 4 plus 1, all divided by 3 times 4 squared plus 2. And so we get 4 times 5 times 9, all divided by 3 times 16, which is 48. So let's, and then that's plus 2. And then you can divide some things out here. The 4 and the 48 divide out and leave me with the 12. And then the 3 divides out there and leaves me with a 4 and a 3. And so you end up with 15 over 4 plus 8 over 4, which is 23 over 4. And remember that 23 over 4 was our right-hand endpoints. I was pointing to the wrong one here. There's our right-hand endpoints there. The 15/4 was the left-hand endpoints. So there you go. There's right-hand endpoints, 23 over 4. All right, so this formula, we could use this formula for any number of subintervals then, and we could get a better approximation. So what happens if we let n go to infinity? In other words, what if we take that expression and we take the limit as n goes to infinity of this expression we just created right here with this kind of long and drawn out process like that? Well, what happens is, first of all, you could evaluate this. This first expression, if the limit as n goes to infinity, and we could multiply this out if we wanted to. You have 4 times 2n squared plus 3n plus 1 all over 3n squared plus 2. And so you have the limit as n goes to infinity of 8n squared plus 12n plus 4 over 3n squared plus 2. And the dominant terms, remember these are limits at infinity. So the dominant terms on that first expression are the 8n squared and the 3n squared. And you can divide out the n squares, and you get that that's going to 8/3. So you have 8/3 plus 2. Whoops, and we've evaluated the limit, so I can erase that. And so what do you get here? You get that the value of this limit is 8/3 plus 2. 8/3 plus 6/3 is 14/3. And so 14/3 is what is that going to be? This is going to be the exact area underneath the curve is our 14/3. And notice that if you go back to these previous problems right here, that 14/3 is between our 15/4 and our 23/4, right, that we got as our original bounds. 15/4 is 3 3/4, and 23/4 is 5 3/4. So we got that the area had to be between 3 3/4 and 5 3/4. And notice that that's what we're getting here, is that this area is equal to 4 3/4. I'm sorry, 4 2/3. Right, and that 4 2/3 is between those two values right there. So this makes sense. And this is actually our exact area. What's happening here is, if we go back to maybe this picture right here, is that what we're doing is we let n go to infinity, the errors become smaller, right? So as n goes to infinity, in other words, the number of subintervals gets larger and larger, the errors in each rectangle, in other words, the amount that's above the curve or below the curve that's an error, is going to 0. And so the errors, as n goes to infinity, disappear. And you're left with the exact area. And so we've kind of hatched a scheme to get the exact area underneath the curve right here. So let's kind of go through this kind of in a little bit more general of a way here. So in general, then if we have this picture right here, we have a curve. Don't know what the function is at this point. It's just some general function. We call it f. And we're looking at the area between a and b. X equals a and x equals b. So we're looking at this area like so. All right, and let's go ahead and shade this in to kind of really make it stand out. All right, so nice irregular region, certainly not a rectangle or anything. So we're going through and using this rectangle scheme that we've just hatched to actually find the exact area underneath this curve. And what we've seen is, first of all, that the area is approximately equal to the sum as I goes from 1 to n of f of a, and a is the left edge of the big interval, plus I times b minus a over n. And b minus a over n, notice that b minus a is the total interval, right? And that's our total width. That's b minus a right there. And what are we doing there? We're taking that and dividing it by the number of subintervals. And that's our delta x. So delta x would be b minus a over n here. And so you have I times b minus a over n, and then this would be b minus a over n out here. Certainly, if you wanted to, you could abbreviate this still further. Instead of writing it each time as b minus a over n, you could write this simply as delta x. So it's f of a plus I times delta x, and then this would be times delta x right here. What do these function values represent? These function values represent the heights of each rectangle. And this delta x represents the common width. All right? So that expression would give us an approximation for that area, and we could make it as accurate as we wanted to by letting n get bigger and bigger. But so what do? We get the exact area by taking the limit of this expression as n goes to infinity. And I'm going to continue to write this as delta x here just to make it a little bit more concisely written. And now this sum is sometimes called a Riemann sum. And what we're doing is taking the limit of a Riemann sum right here. When we take the limit of a Riemann sum, we are getting the exact area underneath this curve. And some notation, this limit of this Riemann sum is called the definite integral. And the definite integral is written using this notation right here. It looks sort of like an indefinite integral, except it has the bounds on the region underneath the curve are written on the upper part and the lower part of the integral symbol. And this is called a definite integral. One interpretation of the definite integral is that it can give you the area underneath a curve that's above the x-axis like this. Now, there are definitely more general ways to write out these Riemann sums. Remember, I am using n subintervals here. Each subinterval is the same width. You don't have to make that assumption, but equal widths in this case is our kind of a simplifying assumption. And we are also using right-hand endpoints simply to make our lives easier, to be honest with you. You don't have to use, you can use any point you want. You don't have to use right-hand endpoints in each of these subintervals. And you don't have to even have the subintervals be the same width. This is simply a simplifying procedure right here that we're using. And so anyway, the limit of this sum we write as the definite integral. One interpretation of this definite integral is that it gives you the area underneath a curve like this. And this curve, notice, is drawn above the x-axis. So, all right, so let's work our way through another example here. Let's look at another function, and let's see how this kind of works out, okay? So we've got one problem worked out, but I did a lot of kind of detours as we went along. So this problem, we're going to start from the very beginning. We have the function f of x is 2x squared plus 3x plus 1. I want to find the area. Let's see, so find the area under this curve between x equals 0 and x equals 3. All right, so that's what we're going to try to do here. So 2x squared plus 3x plus 1 is a parabola, you know, and we're looking at the area underneath this parabola, 2x squared plus 3x plus 1 between x equals 0 and x equals 3. That's what we're trying to find right here. And you can draw this out if you want. You know, you could even just plot a few points. You could complete the square to find the vertex on this parabola if you wanted to do that, certainly. But the curve generally, we're going from 0 to 3, so I'm going to kind of make the scale a little bit bigger here. So there's 1, 2, 3 right there. And I'm going to make the scale on the y-axis bigger also, because f of 3 is 2 times 9 is 18, plus 9 plus 1 is 28. So let's say we go here by fives. So that's 5, 10, 15, 20, 25, 30, like so. So at f of 0, you're at 1. Let me put this in red here. So try it again. So there's 0, 1 right there. At x equals 1, you're at 6. So right about there. At 2, f of 2 is 2 times 4 is 8, plus 6 is 14, plus 1 is 15. So that's right about there. And then finally, f of 3 is, I think we already calculated, was 28. So here's f of 3 kind of sitting up like this. And so you're getting this parabola, or this piece of this parabola like this, right? And we're trying to find the area underneath this curve. And so we're trying to find this area, right? That's what we're trying to do. And so what are we going to do? We're going to use n subintervals, and we're going to use right-hand endpoints, right? That's the expression we've created here, right? So remember, you've got what I wrote on the last page. You have the area is the limit as n goes to infinity of the sum as I goes from 1 to n of f of 0 plus I times delta x all times delta x, like that. Right, that's our general expression. The delta x value in this case is the total interval, which would be 3 minus 0, divided by the number of subintervals, which is n, so this is 3 over n. Okay, so we're on our way a little bit here. So the area then would be the limit as n goes to infinity of the sum as I goes from 1 to n of f of, I don't need the 0 anymore, so I'll leave that out. And this would be I times 3 over n, and then this would all be times 3 over n. That's our delta x. And I'm going to warn you here, this is going to be a yucky expression. So you have the limit as n goes to infinity. I mean, it's already a yucky expression, right? And then times 2 times, 2x squared plus 3x plus 1. So that's 2 times I times 3 over n squared plus 3 times I times 3 over n plus 1. Close those brackets and put 3 over n here. And then I also kind of forgot here, I have to slip this in here. I've got to put that sigma in there, right? Because this is a sum. So put the brackets there. This is a sum. And please don't do that. Don't leave out the limit. Don't leave out the sigma here, because that's what you're calculating. All right, so now what you want to do is go through and do this arithmetic and come up with an expression where you can eventually replace these sigmas with those formulas that I was talking about a few minutes ago. So you just have to be patient and write out the steps for a problem like this. And so you have 2 times that the first term is going to be I squared times 9 over n squared, like so. Plus, and then the next one is going to be 9 over n times I, and then finally plus 1, and that's all times 3 over n on the outside there. All right, so let's just continue to do the kind of do this step by step. Don't do too much in each step because you're going to get lost in here. So this first term, the 2 times 9 is 18 over n squared times I squared, plus 9 over n times I plus 1, all times 3 over n. And then I would go ahead and multiply through by that 3 over n. And we're almost there. We're not too far from this, so be patient. And, I continue. I guess I'm just getting in a hurry here. These should be i's at the beginning. So I could go back and redo this video, but I'm not going to. This is I goes from 1 to n. I goes from 1 to n in each of these steps here. All right, so I goes from 1 to n, and then multiply through by 3 over n, and you get 54 over n cubed times I squared plus 27 over n squared times I plus 3 over n. Okay, there we go. Like that. And then we can split this up. Oh my gosh, this is a really nasty expression, isn't it? And it's the limit of all this stuff, and you have 54 over n cubed times the sum as I goes from 1 to n of I squared plus 27 over n squared times the sum as I goes from 1 to n of I plus 3 over n times the sum as I goes from 1 to n of 1. Oh my gosh. All right, like that. And see, that's what you're trying to get to, because now what you can do is you can use those formulas that I was mentioning earlier, and you can replace each one of these sigma notations with just an expression that involves n. And then we've gotten rid of the sigmas, and then we will be able to evaluate the limit. All right, so substituting those formulas in at this spot right here, you have 54 over n cubed times n times 2n plus 1. Oops, I was writing it in the wrong order from what I wrote it before, so let me write it in the right order, or the same order. So n times n plus 1 times 2n plus 1, that's better, over 6. That's the sum as I goes from 1 to n of I squared. Plus 27 over n squared times n plus 1 over 2. Plus, and then 3 over n times n, finally. The last one's always going to be easy if it's constant like that. So you have that really ugly expression right there. I'm going to go ahead and copy this and paste it into the next page. So I'm going to copy it. I'm going to go to the next page. I'm going to paste it. There we go. All right, and so now the idea is to kind of evaluate these limits, and I think that the thing to do here is to kind of do this slowly and try to simplify each one of these terms as much as you can. So in this first one, the n cubed and the n cancel out, and that leaves you with the 6 in the denominator, so you end up with 54 times n plus 1 times 2n plus 1 over n squared times 6, so 6n squared. Oops. Plus in the next one, the n divides out, and so you're left with 27 times n plus 1 over 2n. And then this last term is just a constant of 3. All right, the 54 and the 6 divide out, and leave you simply with a 9, so that's convenient at least. And so the area here would be the limit as n goes to infinity of 9 times 2n squared plus 3n plus 1 over n squared plus 27n plus 27 over 2n plus 3. Whew. And so remember, you're looking at the dominant terms here. If you want to look at all the arithmetic here, you know, this is 18n squared plus 27n plus 9 over n squared. 27n plus 27 over 2n, and then plus 3, like so. So what are the dominant terms in this first one? This is a limit as n goes to infinity. So this limit at infinity, you look at the dominant terms. And so notice this first one, the n squares would divide out from the dominant terms, and you just be left with 18. The second one, the dominant terms are 27n and, 27n and 2n. So it's the dominating terms there are 27 halves. And then the last is a 3. There's no n's there at all. So you end up with, 36 halves plus 27 halves plus 6 halves. So you end up with 69 halves. Or 34 and a half. And so that's the area of that region right there. And, you know, if we go back and look at this, remember that another notation for this limit of this sum is the definite integral. And so what we've just seen here is that the definite integral from 0 to 3 of 2x squared plus 3x plus 1 dx is equal to 69 over 2, right? We've just calculated that. I'm definitely not saying that these calculations are simple to go through. I will ask you to write out one of these for a polynomial expression like this, very similar to what we've done on these last two problems. I'm not going to ask you anything any more difficult than that. But let's look at just a couple of other statements here to kind of finish out class today and kind of tie some things up here. So let's start off with this integral, the integral from 3 to 7 of x cubed dx. So notice in this case, if you're going to calculate delta x, the interval, the big interval, is 7 minus 3, or that's b minus a, and then the number of subintervals is always n, and so you get 4 over n for delta x in this case. And this would be the limit as n goes to infinity of the sum as I goes from 1 to n of f of, and remember the, well, let's write the general statement out like we've been doing. This would be f of a plus I times delta x, right? So it's that function value times delta x. Remember, these are heights right here for each rectangle, and these are widths, and we've made these common widths. That's why we can write it out like that. All right, so what do you get for this particular problem? You'd have the limit as n goes to infinity of the sum as I goes from 1 to n of f of a would be 3. That's the left edge of the total interval you're talking about, plus I times, and delta x, here's, oh yeah, I've already written it. So here's the delta x is 4 over n. So this would be I times 4 over n like this, and then this would be times 4 over n. Now this would be this is not an easy problem to deal with as far as calculating this limit from here, because you have an x cubed in here. You get a very messy expression. I'm just wanting you to write it out to that point for a problem like this. I wouldn't ask you to do anything more than this. On a graph, this is what we've just done, is we're writing out, or what we're trying to do is get an area, and I'm really kind of changing the scale on this picture, but here is our cube function, right? And what we're doing is we're calculating the area between 3 and 7 right here, right, underneath this curve right here. So this is the area we're trying to write by using this limit, is the area underneath the function x cubed between 3 and 7. All right? Not going to calculate that out. That would be too difficult to do, to be honest, very honest with you. All right, the next problem I want to look at is the integral from 0 to 4 of 2x plus 1 dx. Now this one looks simpler, at least, than the one that we worked all the way through. If we were going to calculate delta x here, delta x would be 4 minus 0 over n, or 4 over n. And this would be the limit as n goes to infinity of the sum as I goes from 1 to n of f of 0 plus I times 4 over n to all times 4 over n, like that. Now, rather than evaluating this, what I want to do in this problem is I want you to look at the picture of the function 2x plus 1 between 0 and 4. So if you do that, let's see, what we have here, at x equals 0, the graph is at 1. And at f, let's see, so we're going to go to 1, 2, 3, 4. We're going to change the scale a little bit and go out to 4 right there. And at 4, you're at 9. So 2, 3, 4, 5, 6, 7, 8, 9. Here's 9 right here. So we're up at this spot right here. And so we're looking at this line like this. And we're looking at the area bounded by that line in the x-axis. And so now between 0 and 4. But what I want you to notice is that this particular region is actually a regular geometric figure. If you look carefully at the shaded region right here, this is actually a trapezoid. right? The area of this region, or this region actually, this region is a trapezoid on its side. And so, you know, if you actually tipped it over, you know, you'd have a trapezoid that kind of look like this, have a very small base at the top like this, and right, we'd have something that looks sort of like that. And so what are these dimensions here? See, the area of a trapezoid is a known formula. It's 1/2 the height of the trapezoid times the sum of the two bases of the trapezoid. And you could, you know, you can write that out in several different ways, but this is the height of the trapezoid, is this distance right here. And the bases are these parallel sides. This might be B2 right here, and then this is B1 up here. And so in our picture, B2 is 9, the height is 4, and B1 is 1. We could actually calculate this really easily. Area is 1/2 times the height, which is 4, times the sum of the bases, which is 1 plus 9. And so you get 20. And because this is a regular geometric figure, we could actually evaluate the limit of this sum, or evaluate this integral, just using a regular geometric figure, that this is actually 20. Now, you can't always do this, but it happened that the region that this integral was describing was an actual regular region like this. Right? So when that happens, you could actually evaluate the integral just by using a nice geometric formula. All right, look at this problem right here. Let's say we have the integral from -2 to 2 of the square root of 4 minus x squared dx. Okay, so let's see. Let's first write out the limit of the sum for this integral. Delta x would be 2 minus -2 over n, and so that would be 4 over n. And so the area as the limit of a sum would be the limit as n goes to infinity of the sum as I goes from 1 to n of f of, okay, the left edge of the big interval would be -2 plus I times delta x, which is 4 over n, all times 4 over n. All right, that would be our expression there. But again, if you know, and that would be a very difficult expression to have to evaluate, because you're going to your function, and think about how this next step would go right here, and this would not be nice at all from here on out. But f of that number, -2 plus I times 4 over n, you'd have to put that into the square root function. So this would be 4 minus x squared, and that would be your x. Is that not so nice expression? And so this is what you'd be evaluating, and that would be a tough sum to have to deal with. We don't need to do that here in this problem, because this is, again, a regular geometric figure. If you look at the region that we're talking about from -2 to 2, so here's -2 and here's 2, this just ends up being a semicircle of radius 2. And so you have this, let's see, something, oh, I know, I knew I didn't do something quite right there. This 2 isn't right where it should be. There you go, there's 2 right there. So now this region in this case is this semicircle. And so we can calculate the area as a nice geometric figure here. But the area in this case would be 1/2 times pi times the square of the radius. The radius of this circle is 2. So it'd be 1/2 times 2 squared. And you get 2 pi as the answer. And so, in fact, that's the value of this limit right here, and that's the value of this definite integral up here. It's 2 pi. All right, so what we've learned today is how to, we've kind of come with a definition for a definite integral, first of all, that it's a limit of a Riemann sum, and that one interpretation of a limit of a Riemann sum is the area underneath a curve that's above the x-axis. Now, we have a lot of things to look at here. First of all, there's other interpretations for the definite integral. What if the curve is not always above the x-axis? What if it's below it? What if it's sometimes above, sometimes below? There's all sorts of considerations that we have to deal with. But this gets us a good start into the idea of what a definite integral is, and that the definite integral, one interpretation of the definite integral is that it gives you the area of a region bounded by a curve if the curve is sitting above the x-axis. So we will explore the definite integral further and try to find some more efficient ways of evaluating definite integrals. We've looked at 2 ways so far today. One way is to go through the limit of the sum process and actually calculate the limit of the sum, which is a messy algebra problem. And we've also seen a few examples here at the end of regular geometric figures. Well, the first one's not always going to be practical, and the second one won't always be possible because you're not always going to get a definite, nice geometric figure. So we have to explore other ways to evaluate these definite integrals, and that's what we'll be doing next Monday. All right, so please don't forget your homework. Your homework 4 is due on Friday of this week, not today as originally stated, but on Friday by the end of the day. So please email that to me. Take advantage of my online office hours, and have a great week, and we will be in touch. And remember, I will be posting exam 2 grades later today on your D2L grade book. Have a great day.